right, we're recording.
All right. Well, welcome to another episode of MatMul Cast. This time, you might notice that we're coming live from the real world. So,
Yes, in person. Yay.
yeah. And we wanted to talk about the namesake of the show, right?
Yes.
So, what is MatMul? What does that mean? Why is it important? And what do we do with it?
Yes.
That kind of stuff.
Yes. So MatMul comes from matrix multiplication. And what else?
Well, what else do you need? Everybody understands already, right? It's used a lot these days
Mhm.
for these things you might have heard of, like machine learning and artificial intelligence.
Mhm.
They use a lot of it. Why do they use a lot of it? Do you know why?
Okay, that's a big question. Now it has, like, in my head, there's so many threads going on right now.
All right.
Like there is, like when I look at matrices, I think of I don't know, linear equations. I think of graphs. I think of um
So it sounds like there's a lot of different things.
there's so much right now. Like
Maybe it would be better to like explain what it is first before we dive into like why it's used.
when you say what it is, you mean what matrix is.
Yeah, let's start with what is a matrix?
What is a matrix? Okay. So how do you think
Oh,
of
okay.
a matrix?
So I was just talking about this morning in a class I'm teaching, but um, something similar, not exactly, but anyway.
Hmm.
Uh, so you know how you can have a thing? Well, turns out that having just one thing is pretty much like a special case of having a lot of things. And having a lot of things in a regular grid or regular pattern is a very convenient way to think about a group of things.
Hmm.
So, for example, if I have, I don't know, 6 cans, and then I arrange them, packed them together really closely, then I could think about, oh, I've got 2 rows, and each of those rows has 3 cans in it. And by arranging them like that, I've sort of simplified all the possible ways I could have an assortment of 6 things into one very compact representation. And I can describe the representation really simply by saying it's 2 by 3 cans.
Interesting. Because you just summed up the essence of abstraction in a nutshell, which
I
is
don't know what
crazy.
that means.
I'll explain what I mean. So what is a number three? A number three is essentially three things, which the thing could be anything, right? So I'm quoting from Three Blue, One Brown video of Essence of Linear Algebra, right?
It's a good one.
So that's how, yeah, I love that. And it, what it means is mathematicians found a tool to abstract. It doesn't matter whether you have 3 laptops, three of anything, like 3 people. The number three is an abstraction that captures 3 quantities.
Yeah.
Similarly, a matrix is a representation that kind of captures an abstraction of what you just said, things in a pattern, in a way, and that's a tool that mathematicians use.
Yeah, for me, the thing that makes a matrix interesting is that it's a very rigidly constrained way of holding those different items together in a group. Like you could have, one thing over here and another thing over there, and then just sort of strewn about, like, and you got your clothes all over the room. There's no order to them. You just throw them into a pile. But if you arrange things in a very like orderly manner, then it makes it somehow easier to think about what's going on in that situation. Like I can look at a group of 2 by 3 cans, or like a grid of pixels all arranged somehow, and say, oh, that's one thing, which is a group of things, instead of thinking like, oh, that's a big mess with randomly arranged items inside, I can think that whole group, I think of the whole thing as one unit.
Right. And it's crazy that you mentioned pixels, because now that brings me to another concept, that a matrix could mean different things for different people. Like, you're a computer scientist,
Right.
and
So are you.
yes, yes. And for us, it could mean pixels. It
Yep.
could mean a multidimensional data, right? But when a physicist would think of a matrix, they would think it in terms of vectors, in terms of equations, and those equations would have like a spatial existence.
Yep.
In
Like you can describe the system using a system of equations. You can
Yes.
describe like the ball falling through the space, or two things orbiting each other with a system of equations.
Yes.
Which is often written in matrix form.
Right. And a mathematician, like from where we started, would have an abstract sense of a tool that captures almost everything, like a perspective of a physicist or a computer scientist, so that they can manipulate that representation with a given set of rules, right?
Yeah.
So, like,
we're very abstract right now.
Yeah, I know. But what I mean is, the given set of rules that I'm talking here would be like, how do you add two matrices? That would be something that a mathematician came up with to capture the essence of a matrix,
So,
right?
like, let's make it a little bit more concrete even than that. And let's say, like, when you think of a matrix, do you think of it as having a specific number of dimensions? Like I do. Like the word matrix in my mind makes me think two-dimensional. Like it has columns and rows and no other way of describing a shape, right?
I see. Yes.
You've got a number of columns, you've got a number of rows, it's rectangular, the end.
Oh, I see a matrix sort of like a little differently. I see a matrix in terms of multiple vectors, and each of the vectors are the columns of the matrix.
Okay.
And so I usually look at a matrix multiplication as a transformation, like when you're as a linear transformation, to be exact. So when you are and this is mostly a physicist perspective, because like I'm a fan of 3 blue 1 brown, so
Right.
It's also coming from that source.
Okay.
But it's like a concept where whenever, if you're considering a Euclidean space, right? In a two-dimensional space, if you have a vector, you have the coordinates of that vector with the assumption that your basis vector, which is the unit vector I and j, I hat and j hat, being 1, 0, and 0, 1, right? For the x-axis and the y-axis, and whatever coordinate system, coordinate values of that vector would depend on that basis vector. So if you have some sort of transformation of that vector, let's say you skew the entire plane, you bend it, so that bend would be can be represented as the value of I hat in the first column of the matrix. When the matrix was bent, where does that I hat land on after the bending? Did that make sense?
Kind of.
So let's say you have a square piece of paper, right? And you rotate it by 90 degrees.
Sure.
Like your axis, entire axis shifts. now your I is pointing towards your left
Okay.
and J is pointing up,
Right.
right?
Okay. So now I can imagine there is some function that takes an I that used to be here and makes it over there.
Yes, but that function is essentially the new matrix where the first column of that function is the value of I vector, and the second column of that function is a J vector. So that matrix, which is a concatenation of two vectors I and J, is essentially representing a transformation of that.
That's pretty wild.
Yeah. And then with this matrix, this transformation, you can essentially look at any vector that its values, you can extract any values in the Euclidean space of any vector. Let's say after the transformation, a vector lands up at coordinate 3,3 after that transformation.
Okay.
How would you calculate, or how would you picture that vector before the transformation? You can do that. That matrix becomes your function of that transformation. You just multiply through that matrix.
So maybe we should say, what does it mean to multiply a matrix by something?
Oh yeah. So
that's
with
the mole part of the
right with my transformation with a view of linear transformations as a matrix, the MatMul would be sort of the mat part would be the transformation of the bending of space, and the multiplication of a vector to that transformation would be its existence or its values before the bending. I am not.
It's still super
sense.
abstract.
Yes.
To me, I was thinking like, for someone who just never heard the word before, like mechanically, when you're trying to say, okay, I've got let's say a vector,
okay,
and a matrix, and I want to do a matrix multiplication or a vector matrix multiplication.
Right.
What are the steps that I do in order to get some result? So let's say I've got a vector A, which is 3 elements long, and I have a matrix B, which is, well, what should the dimensions of that be?
I see. Let's do this.
Do we need paper?
I have an iPad, so we can screen share while
Okay,
writing on it.
There's a specific mechanical sequence of steps that most people understand to mean when they say, well, most like mathematicians, they mean the same thing when they say matrix multiplication. They mean do these sequence of steps in this order,
right?
And then you'll get some results, and we'll call that a matrix multiply. Like you can't just decide, oh, I'm going to multiply, the middle element of my array or my vector,
right,
by the last element of my matrix, and then I'm going to skip somewhere else. I'm going to multiply this other thing by some other thing, and then I'm going to skip a few elements and just not multiply them at all, and I'll call it done. Like, no, we have an actual, like a formalized,
yes,
or very like rigid thing to do, and we call that thing matrix multiply.
Yes, and
it has a special look to it too.
Right.
And it turns out that like the shape of the two things that you're multiplying is really important.
Yes, and it'll be clearer if we do it here, and I'll let you start.
Oh, okay.
Sure.
Oh,
I'll do that.
no, that would be too easy.
Why?
You must pay a tithe to Apple before you may proceed.
No, I do this
Just
all
say
the
3
time.
good things about Apple on social media, otherwise this won't connect.
Sharing.
That's silly. Apple wouldn't do that. Microsoft and Google might, but Apple wouldn't.
AirPlay. Okay. Why is that not
It says
working?
it's unable to. I think he just doesn't want to.
I may have.
The problem is you tried to run Emacs at the same time.
Do you by any chance have a USB-C wire in your backpack?
Not the kind you want, I don't think.
USB-C to USB-C.
No,
No?
I don't think so. Maybe in a very roundabout way, although I don't think it'll work. I think this is going to be not quite what you need.
Oh, that might work.
It might, but I kind of doubt it. So like maybe plug that into your
Yeah.
laptop, so it goes
Goes here.
and then plug this end into the iPad, right? Yeah.
Okay.
And then the magic smoke comes out.
Okay.
No,
Here.
not that side.
Right.
Over that.
Now, you share.
Press this computer.
Sure. Okay. Pressed.
That's good.
All right, we're in.
That
We're
was
sharing.
so easy. It
Yes.
just works.
Yes.
All right. I'll get this wrong because it's been a while since I've actually done this
Mhm.
on paper.
Well, we'll do it together.
All right. So
Yeah.
let's say we've got a vector. Oh, nope. I'm going to draw it in
No,
white
do it.
on a white background. Okay. So we've got, I'll write it like a Python list.
Okay.
This is a vector. And we have a matrix, and our matrix is going to be shaped a little bit differently. Let's make it like a small. Did I do it right?
Yep.
Okay, good.
I think it needs to be
Turned a different way.
flipped. I think. Wait,
So
this
I'm not
is
sure.
1, 3, and this is 3, 2. Yeah, it'll work.
So this is, all right, so when you said 1, 3, what you mean is the shape of this is 1 by 3, meaning one row. If I'm looking at it from that direction, I see one
Yes.
thing. And if I'm looking at it from this direction, I see 3 things. So 1 by 3. And this one has a shape of, I'll do the same thing where I first look in this direction and I second look in that direction.
Yep.
So if this is 3 by 2.
So 3 rows, which is DE is the first row, FG is the second, HI is the third,
Right.
and 2 columns, which is DFH and EGI.
Right.
All right.
And now we are allowed to multiply these things together because these 2 numbers are the same number.
Mm-hmm.
And that works because the thing we do is we first take this thing and we multiply it by that thing. And right?
That might be right. Yeah, go on.
All right, I'll just continue and then you can
Yeah,
you can
yeah,
go with it.
yeah.
Okay. Second thing we do, so we get AD
Mm-hmm.
for one thing here. And I'm pretty sure the next thing we do is B times F.
Yes.
And the third thing we do is C times H. And what do we do with these 3 things? We add them together.
Yes, that's right.
And then, so what do we get out of this? We get a single number.
Mm-hmm.
This all adds up to a single thing. Let's call it J.
Mm-hmm.
We do the same thing for ABC, but this time we go into this other column and do AE plus BG plus CI. We'll call that K. So we end up with 2 numbers after
Right.
all this.
Right.
And those numbers go in a certain place. We want to end up with a shape which is 1 by 2. So we end up with a shape like
Oh, the page ends there.
Oh, okay. We end
So
up with
you'll
a
have-
shape that is this shape. First we have J, and then we have K.
Yes.
So this is the shape 1 by 2.
Yep.
Okay. Phew. I was so nervous that I was going to do it backwards.
No,
Right.
it's just the way I have, like, it's exactly the same thing. With the only difference is it's hard for me, my brain, to remember these steps where I'm doing individual elements.
Mhm.
So the way I remember it is I take this column and multiply with this column,
Yep.
this row.
And now you don't have to think about which one's oriented and what.
Yes,
way.
and this automatically corresponds to this multiplied by this multiplied by this. Basically, I place this entire column on top of here,
Mhm.
which makes it D, F, H, and I multiply these
Each item gets
item
multiplied by the corresponding item.
add their sum,
Mhm.
which gives me exactly this.
Yeah.
Um,
And then you just do the same thing as long as you have any more columns left in
yes,
your thing.
yes. So this was a vector matrix multiplication.
Right.
Yes. Now with a slight variation,
Yeah, you want to do like a matrix multiplication?
yeah, okay.
Because I guess like if you say, if you were to reverse those two things and said, instead of going vector matrix, you went matrix vector.
Yes.
That's not very interesting. It's basically the same thing, right?
right.
Yeah.
Right. So for
but
a
if it's
matrix,
then it's
matrix,
slightly more interesting.
yes. A, B, C, D, E, F, G, H,
I
I.
thought you were a column oriented kind of guy. Why
What?
why are you labeling them from left to right first?
I don't know. I
All right.
didn't think
It's okay. I just
I,
wondered.
J, K, L. No, I was always a row major.
But didn't you just said like when you were describing what you think of as a matrix, you think of it as a group of columns?
Yes. So,
I'm getting you off track, sorry.
no, that's completely fair. But so that concept for me is just to have an intuition of what that matrix really is. But when I'm doing math, I was not originally trained to think of a matrix to be anything. It was just math and numbers.
Mhm.
And originally I was just trained to think of them as computation.
Mhm.
So a matrix,
For the record, I think that's the right way to think about them. I don't think you should think about them in terms of how they're stored in a particular computer implementation,
right,
because that could change someday.
right.
We don't want to get locked into
And
this is the way it must be.
I think we should talk about how they're like
Oh yeah.
right now we're just talking about matrices,
Start from
and
the math and
how
the
they
pretty
are.
pictures.
right? And
We'll get
then
into
we
the
can
ugly
see how
detail.
a computer interprets and
Yeah.
and stuff. So yeah, for me, like when I'm doing a computation, it's just a bunch of numbers.
Mm.
But the column major aspect, where each of these columns are individual vectors, I'll get to that in a second. But that gives me an intuition when what it means to multiply in spatial sense.
Mm.
Like physically, what does it mean when we multiply a matrix? What is its significance in our physical world?
Okay.
So JKL.
Notice that you're doing a 3 by 3 for your second matrix.
Oh yeah, I'm digging a grave here.
It'll be
But I don't even have to do it the entirety.
all right. So
fit.
now, before we had a vector, and we multiplied that vector by a column,
Yes.
there was no other choice, right?
Yes.
We had to take the whole vector,
Yes.
multiply it by the whole column. Now what do you do? Because you got multiple choices now.
So remember how we took this entire column and placed it here
Mhm.
for the first value, this one, and for the second value, we picked this entire column and placed it again on this, multiplying each
Yep.
elements,
item-wise.
yeah, item wise, and then summing them up. So here we do the exact same thing. We multiply this column
This is gonna be
by this
absolutely
row.
terrible on audio only format.
Yeah, I know.
Go to the YouTube for this one.
Yes, please. We apologize.
But imagine I'm drawing a rectangle around A, B, and C. Okay, there you got it. Perfect. You're following along just
yes. So the first column of a matrix, the second matrix with the row of the first matrix.
okay.
So, which means A multiplied by J, B by M, and C by P. So let's write that down. Before doing that, let's see what the shape of the first matrix is. It's 3 by 3, and the second matrix is also 3 by 3.
So right away, before you even do any computation, do you know what the shape of the result's going to be?
Yes. Yes.
All right, well, what is it? How do you?
So
Yeah,
first of all, the matrix multiplication can only happen if the inner two numbers of the shape.
meaning if you were to describe saying the number of rows first and the number of columns second.
No, the opposite. Number of columns of the first and the number of rows of the second.
I was going a step backwards. When you say 3 by 3,
oh yes,
the first 3 describes the number of rows. The
yes.
second 3 describes the number of columns.
Yes, exactly.
So, like a 2 by 3 is wider than it is tall.
Yes. So the shape, when we're writing a shape of a matrix, that's the steps we follow. The first, the 2 by 3, which is a wider matrix than it is tall.
Yep.
The 2 is the number of rows, and 3 is the number of columns. Now, in order for any matrix multiplication or matrix vector multiplication to happen, we first look at the shapes of the two things. For this purpose, let's even consider the vector to be a matrix of one row.
Yep.
So we look at the shape, and the number of columns of the first matrix should be equal to the number of rows of the second matrix. Right? So in this case.
Yeah, so, and actually, I want to jump in here with a way of describing these things. Because when we're just talking about matrices, it's sort of easy to just get locked into the terminology of rows and columns. But if we're talking about, you already made a little bit of a concession here when you said the vector was a 1 by something matrix. Well, it was a vector, right? At first, and then we just decided to call it a matrix.
That is true.
By adding a completely redundant 1 to its shape, right?
Right.
We could add as many ones as we want, right? It's a 1 by 1 by 1 by 1 by 1 by 3.
Yes.
Whatever dimension thing that is.
Yes.
We don't have good words for them after we get, matrix. We have vector for 1-dimensional, matrix for 2-dimensional. And then we kind of just ran out of good words. So mathematicians these days call all these things tensors, right?
Oh.
So a tensor is a thing like a matrix or a vector where you just aren't really caring about what to call it, and it can have any number of dimensions.
I see. I did not know that. I always wondered, and I never got time to research into that what is a difference between a matrix and a tensor.
Yeah, a matrix is just a kind of tensor.
Okay.
It happens to be a 2-dimensional tensor.
I see.
And then, some mathematician may argue that there's a better definition for tensor, but that's how I think about it.
I see. And is there a difference between, now I'm going to do a sidebar because I'm curious.
Tangent on a tangent?
Yes. Yeah. Is a tensor different than an array?
I think, well, for me, pragmatically, I would say an array is yet another kind of tensor, just 1-dimensional.
No, what if the array is like a multi-dimensional array? Is that array different than a tensor?
Multi-dimensional array where you can describe the shape with, like, it's a 2 by 3 by 5. I would say that is a synonym for a tensor.
Okay.
They're the same.
I see.
You call
now
it tensor?
I have one more question, which is completely different than what we're talking about. NumPy array
Mhm.
and a PyTorch tensor.
Same.
Same thing? Are they synonymous?
I think in fact a PyTorch tensor is implemented with a NumPy array inside
Hmm.
and some extra information.
I see. Okay. All right.
A little bit of metadata that lets PyTorch do gradients on it.
Good to
more
know.
efficiently.
Okay.
Yeah, the same thing. And
Mhm.
this is where I was trying to go or what I had in mind at first was the name we give for that first number in 3x3.
Mhm.
I would call that the first axis. The first 3 is the first axis. Second 3 is the second axis.
Okay.
Or another way, a lot of people, like mathematicians especially, would call this the dimension. We call this the first dimension and the second dimension.
Mhm.
If you have a 3x4x5, the first number you say, the 3, is the like the leading axis.
Okay. All right.
And this is not very important for matrix multiplication,
Mhm.
but it becomes extremely important when you want to multiply things that are more than 2D.
I see.
Because then you need to figure out, okay, what am I doing here? I don't just have rows and columns anymore. I've got a bunch of columns.
Right.
So how do I start? And this gives you a sort of like a foundation for, okay, if we use these terms and we call it like these more abstract, we just got a little bit more abstract, that means we can apply that same procedure to any number of dimensions.
Right.
Mosquitoes everywhere.
Yeah.
Get up.
And okay.
So yeah, do your
So
multiplication.
for the matrix, we're dealing with a two-dimensional matrix because, as you said, these are the dimensions and we have two of them.
Right.
And with what you just said, we can apply the same set of rules for any number of dimensional data that we have.
Mhm.
And this data that we have here is a two-dimensional data.
Yeah.
Okay.
So I think doing another example of like the matrix multiply it'll be good. Because
Okay.
then we could have another concrete example. What happens when you have a 3x3 multiplied by another 3x3?
And the next example, we can not use the square
Yeah.
matrix. Okay, so here in this case, I'll just pick the first column of the second matrix and multiply it with the first row of the first matrix. So if I were to write it,
that's going to be
would
like
be
AJ
plus
BM.
BM plus CP. And
that adds up and it turns into a single number. Where does that number go in your result?
Right. This number, basically the product, the dot product, no.
It is a dot product.
It is a dot product?
I think so.
Okay.
It's a dot product with two one-dimensional things. So it's like vector dot product.
Yes, yes. So this dot product of these two matrices, we already know by just looking at their shape that the result is going to be a 3 cross 3, which comes from,
those are the leftover numbers from the two shapes.
Yes.
After you put them next to each other,
Mhm.
make sure first matrix and second matrix, you put their shapes next to each other. The ones that are close together have to be the same.
Yes.
You just, so they drop out of the whole thing, and then the thing you're left with, that's your result shape.
Yeah, so the thing that drops out makes the multiplication happen are these inner dimensions of the shape, which drop out. And what's left is this 3 and this 3, and that's the result of the matrix. So,
all right, so where does your first product go?
So first product goes in the first position, first element of the resultant matrix.
Okay. That makes sense.
So
maybe it's not quite obvious though. Where does the second product go?
Let's say this is no, this is capital A, right?
Oh, right. Well, if you're using a capital letter and you're reading a math paper or you know that they use a capital letter to refer to the entire matrix, right?
Yes, you're right.
If you're reading academic papers, you just have to know this, or you have to have a teacher that you can ask all these questions to.
Like, so let's
what
call
if it's capital and bold and italic. It's like, oh well, that's actually that's something else entirely.
So let's say this is what, I don't know, XA.
Ooh, okay, yeah, that works.
All right. So this would be the first element of the result matrix.
All right.
Or we can just say x1. X1.
That works.
All right. So that was the first element. The second element would come from multiplying the second column
Of the
of
second
the
matrix.
second matrix with the first row
Okay.
of the first matrix.
So we're still on the first row of the first matrix,
Yes.
but now we've moved on to the second column of the second matrix.
And that would come out to be x2, which is here,
Okay.
and that would be this
So,
one to this one. So it would be,
so you got a 3 by 3 by multiplied by a 3 by 3, and so your second multiplication that you did here was the top row of the first thing multiplied by the middle column of the second thing, and your result goes in top row, middle column.
yes,
This sort of makes sense now.
yes.
There's enough things here now that you can actually see the pattern starting to
Mhm.
emerge.
And similarly for the third one, it goes, oops, wrong one.
Mhm.
The
Third
third
row.
column
Oh yeah.
of the second matrix with the first row. So the column of the second matrix decides the column placement in the result, and the row of the first decides the row in the result.
Yep.
Right? So this multiplied by this goes as x3 here.
It's really unfortunate that row and column are not ordered alphabetically,
What do you mean?
because the row comes second alphabetically. R is after C.
Oh yeah,
So you just have to remember,
right.
just yeah, don't try to come up with a mnemonic for this. Just always
Ooh, there
memorize.
are these. Are these mites? Termites? I don't know.
There's a bunch of nature out here.
Yes.
So cool.
So okay. So now we have a pattern. All we have to do is this goes second row here,
Yeah.
which becomes
We know where that result's gonna go.
x4, then second,
Nope.
oops, second, nope. Second column with the second row gives x5. Third column with second row gives me x6, and so on.
All right.
So now we have, see, I didn't have to do the entire thing.
Good.
I cheated. All
All right.
right.
So this is the mechanical, demonstration of how do you multiply two matrices together. And it's probably, we don't have to continue with like a 2 by 3 multiplied by a 3 by 2.
I guess. But the reason what's important here is our podcast is named MatMul because I think it's safe to say that this operation is the most widely used operation in not just computer science, but in science in general, because most of the science is done with computers. And for
Well,
okay,
it's a widely
it's
used.
in numerical analysis.
You know what I would say though? I would disagree slightly and say it's not so much like it's a fundamental operation. I would say it's the most fundamental algorithm. Where I'm sort of drawing a line between something like addition,
Right.
simple addition. That's not fancy enough for me to call it an algorithm. But matrix multiplication is just fancy enough for me to think that's an algorithm. There's a sequence of steps involved.
Right. And it's such an important algorithm that a lot of, and it's so often used that modern computers have a dedicated hardware unit to do this algorithm. And even though I see what you mean that it's not an operation, it's an algorithm in terms when we're thinking in terms of a math, but modern computers have this as a primitive operation, a matrix multiplication.
Well, I mean, I know enough about like x86 instruction set to think that that's not saying that much. Because-
Not the CPU, but I'm talking about a GPU.
Okay,
So for a GPU,
all right, so
um,
GPU, that's a different class of
yes,
machine,
yes.
right?
So when I say modern computers, I mean, so I consider CPU a little, well, that's not fair, honestly, but I'm thinking as we've progressed in computer architecture world, we've sort of progressed from the only CPU to a more heterogeneous line of computing
Oh,
where,
that's certainly fair, yeah.
yeah,
'Cause
and that's why I think of a GPU as an evolved. I know it's not completely true, but
it's one of several different types of
yes,
machines within a modern system.
yes.
Like you don't just have a GPU, you don't just have a CPU, you have both, and maybe some other things as well.
And we call them accelerators right now.
Hmm.
And
Because they make some part of your program go faster,
yes,
but not the whole program.
right. And these accelerators have this matrix multiplication as a fundamental primitive operation. Because like if you look at the GPU architecture, they have like a MatMul unit.
How does that work? Does it have a specific size?
Yeah, it does.
So it works, it does like, it'll do MatMul for your whole matrix if your matrix is small enough, and otherwise it has to chunk it up into little pieces.
Yeah, so
Okay.
I know how a GPU does it.
Oh my
So
God.
a G
They're everywhere.
a GPU has like so technically a GPU is a little different from a CPU in terms of instead of having like 4, 8, or 64 cores, it has like tens and thousands of cores.
Mhm.
So each core has a matrix multiply unit. What it does is it takes that entire bigger matrix and chops it off in smaller square blocks
Oh, yeah,
of
because
matrix.
what you've done here by demonstrating on the iPad is
Mhm.
I mean, what you're saying the GPU does is it takes advantage of the fact that each one of these A times J multiplications can happen completely independent of all the others.
Yes, and we can
That's
actually,
important because then you can do them all at the same time.
yes,
You're not waiting for A times J to get done before you can multiply B times N, right? You
right.
can do them at the same time and it doesn't change the result at all.
Now I'm a little nervous in writing that down and showing the parallelism how it'll work,
Well,
but
you do have to wait for all the summations to finish
yes,
before you get your final answer. But that itself is also something you can do. You can do each summation of those three things independently from the other summations.
say that again.
So you got this first row here of summation, like this one.
Uh-huh.
You can do that sum independently from this sum.
Yes.
They can happen at the same time.
Yes.
Yeah.
Yes. Yes. And that's how
You do have to do the multiplications first before you can do the sum, but you could batch up all the multiplications, get them done, and then you could batch up all the sums and get those done.
yes. And that independence of operations sort of gives the GPU edge because it has tens and thousands of cores doing all of them at the same time.
Mhm.
That's why we can have those crazy modern games with near realistic renderings.
Because the screen is basically a big array, 2D array of pixels, or
Yes.
it's a matrix of pixels.
And just to give you a perspective, the modern 4K display is
A lot.
a lot of pixels. It's like 4 times 1024. That's the 4K aspect of it. Multiplied by what's the width?
So the 4K, that's how many rows tall the screen is, right?
Yes, and what's
The
I
width is
think the
like
column,
bigger usually.
yeah,
So maybe just make it easy. Let's call it 6K.
yeah,
It's probably bigger than that, but
and yes,
so you got you know,
So,
roughly 4,000 times 6,000, which is
yes,
24 with 6 zeros, so 24 million. And then each one of those pixels
has 3 RGB in it.
yeah, so red, green, and blue, which is usually like 24 bits.
Mm-hmm.
So it's not quite evenly split because we give more bits to the green because our eyes are more sensitive in that part of the spectrum.
Oh, I did not know that.
I think it's like, I'm not really sure.
Hmm.
Now, like, if you know those like hex color codes from the web, it's just like 3 pairs
Yes.
of digits.
Uh-huh.
Um, that is not split up the same way. But I think if you got 24-bit color, you could divide it evenly to like 8, 8, and 8.
Mm-hmm. I see.
Which I think is maybe that is what they do. But I feel like at least some systems give a couple more bits or maybe 1 or 2 more bits to the green.
Okay.
I could be wrong about that.
I
Anyway,
see.
but the point is,
There's a
you got
lot
that-
of data.
yeah, that 24 million pixels times 24 bits. That's how many individual bits you got.
Yes.
So I can't do that
Oh.
arithmetic. It's too big. It's a lot.
And yes, and it's not just one matrix. And then you have the concept of frames because it's all moving in real time. So now you
Yeah, you gotta
have
do
like,
that whole big calculation of that giant matrix 60 times a second.
yeah, 60 times a second. And then you have
Suddenly-
to account
yeah.
for the refresh rate, which is this, but also like,
the game has to do something interesting in that
yes,
time as well. So suddenly performance is extremely important.
yeah, and you don't know what is your transformation matrix. Is it exactly the size of the screen? So how you're changing each pixel, if you're changing all the pixel with respect to a very complicated function, so the matrix that you're multiplying with this giant matrix could also be the same size, which just,
Yeah, I feel like 2 things happened to evolve like it's like co-evolution of these 2 different concepts. So
Mhm.
one is people recognize that I can make something appear on the screen the way I want it to by doing a matrix multiplication.
Mhm.
So the theory says, hey, if you do this multiplication, you get this result. Maybe that's what you want. Maybe it changes like the perspective in your 3-dimensional scene, or maybe it changes the lighting or something, or you've got all the pixels in your screen, are, here's one, like you've got a water texture that's supposed to look like it's got ripples going on it. So that would be really intensive to compute the physical simulation,
right,
but you can make it appear like it's rippling if you give each flat tile of the texture of the water a pattern to play over and over again. And then you can just say, okay, well, the pattern I need to do is I go to this point in the pattern and I put that, I update my tile to show that part of the wave. I do that for all the different tiles on the screen. They're all at different coordinates, but I can use a matrix to say exactly where they are and make the update to each tile that I want.
Is that a concept of a kernel? Like where
Maybe
the pattern that you mentioned here becomes a kernel, and that function is a smaller function that's applied to the chunk of the bigger matrix that we were talking about.
Yeah, I think so. So this theoretical kind of innovation happens, and then at the same time, or happening kind of concurrently, hardware is being developed that can do a matrix multiplication more efficiently, and multiple cores are being developed where you can have like an extra computational element that is just sitting there waiting for something to do, and you notice, hey, this matrix multiplication thing, I can do that all at the same time. I don't have to wait for the other cores to finish. So let's get them all working at the same time to solve this problem. And so those 2 things kind of feed back on each other, and then you get demand for bigger and bigger GPUs with more and more cores, and you get bigger screens with more pixels, and then you get faster games.
Right.
And it kind of, it's a
For
positive feedback loop.
and for the scientists out there, it would be more and more simulations or bigger and bigger simulations.
Yeah. It's like a GPU was originally for gamers,
Right.
and now it's not just for gamers.
Yeah. I think the first time GPU became for non-gamers was in the year 2001. I think the NVIDIA line of GTX 285, I think, came
Yeah.
up with the first general purpose
Right,
GPU.
because at first they were just very, very focused on what does the game need to display its graphics? Okay, we'll give you a function for that. And then gradually people are like, I kind of want to use this for more things than just games.
Right.
So they started to make the GPUs themselves became a little bit more programmable, and then a little bit more. And then like what you're saying is
And that's why the transition that we called them graphics card
Mhm.
kind of changed and shifted to a general purpose, even though the name graphics processing unit stayed, but they added this general purpose
Yeah.
as a prefix that it's not just a graphics
So now you can
processing
have
unit
a
anymore.
GPU.
Yeah. Nice. It all lines up.
It does.
Um,
Now, one thing that hasn't quite caught up yet is
Mhm.
programming languages.
yes.
The way that the person who's developing applications for this hardware, it's not quite caught up with the hardware itself. I
That
would
is
say.
true. Yeah.
Like, how do you program a graphics card? Well, you use CUDA, which is basically like C, which is basically like do one thing at a time language.
Right.
And the GPU is just sitting there waiting for you to tell it to do, 4,000 things at one time. So
Right.
C has no way to express that. So you end up with like things like CUDA that try to say, okay, well, it still looks like C. So all you C programmers, you can still feel comfortable. But then we add these little features to make it work
Right.
more effectively with the graphics
And
processor.
and CUDA is sort of, it has its limitations because even though it's state of the art, but it only works with NVIDIA GPUs.
Yeah, that's a pretty
Uh,
big limitation, right?
right. And then I think the OpenCL is like an open source version of that.
Something like that. I don't really know.
But then
Probably know
there's
more than I do about that.
but then there's like these intermediate options like OpenACC,
Hmm.
which is essentially not telling the GPU how to run its code. Like CUDA tells the GPU how to run code, right? But OpenACC, on the other hand, just expresses a code in terms of do this in parallel. It doesn't care how many cores there are. It doesn't have to do all that math. It just recognizes that it's a directive-based programming language where it recognizes a parallel computation and offloads that computation to a GPU.
Okay. Now,
And it's all initiated by the host, which is like the CPU allocates memory in the host. It um it it initiates the computation and then it does the garbage collection too. The CPU is doing all of it for the GPU. I think that's a major difference. I could be wrong here, but I think
So
CUDA does that all on GPU.
okay, there's one thing that you said that I'm going to kind of try to latch onto. Now, as someone who knows nothing about OpenACC, when you said that it recognizes a part that can be parallel,
Yes.
does that mean you write code without regard for parallelism, and then the job of OpenACC is to find the parallelism in your program?
Oh, sorry. No, I get the confusion. You're right. OpenACC does not do that. The programmer who's writing in OpenACC, it's very similar to OpenMP, but
okay, like a pragma on top that
but
says,
the GPU version of it, so the programmer will say, this for loop is parallel. It
Okay.
can be parallelized. So the programmer can just do pragma.
Okay.
Yeah,
So you
that.
have to explicitly annotate in your program that this part, you're just giving a clue to the compiler or something that says, hey, this part should be parallel.
Right.
Okay, I see what you're saying.
And with this kind of limited scope where you don't have control over, you need to run this code in this particular, like, GPU has a lot of hardware in it,
Yeah.
and CUDA kind of gives you control to that much hardware. OpenACC, on the other hand, does not do it exactly that way.
Well, it's trying to be a little bit more abstract than
Yes.
just CUDA, right? So
Yes.
CUDA is like vendor specific. It can make, and it's for maybe for lower level control of the hardware.
Yes.
Sounds like OpenACC is trying to be a little bit higher level and a little bit more like vendor independent.
Mm-hmm.
Okay.
And I think OpenCV
Yeah.
is
Computer vision.
no. What's the AMD version of it? I think there's an AMD version of it, and then there's like the Apple version of GPUs. I think it's
Yeah.
called Metal.
Yeah. And there's something like AMD has something like Rock or something like Open Rock.
Okay.
I don't remember.
Yeah. So basically,
We're butchering it. Sorry.
yeah. But all of this is essentially ways to program GPUs. And the reason we are talking so much about GPUs is because they are extremely optimized to do matrix multiplication.
Yeah.
All
right, there's two little things I want to say before maybe we
yeah,
wrap it up.
Yep.
One is annotating a C-like language to tell it where it can be parallel. That's one way of approaching a problem. Another way is have a language which is only parallel. And therefore, there can be only, there's no need to annotate. You can only express things in a parallel way.
Right.
There are languages like this. They just happen to not necessarily target GPUs.
I see. Can you give an example?
Yeah, the array languages like APL,
right,
BQN, Q, K, J, all these one letter and up to 3-letter names of languages. They're parallel by default, parallel by construction. So any expression you write is inherently a parallel algorithm.
I see.
Now, there is one APL compiler that does target the GPU, and it even runs on the GPU. So that's a pretty novel thing. Most compilers are very like branchy tree traversal type of things, but it turns out you can express that as a data parallel algorithm as well.
I see.
Anyway, so that's one tangent. Did you have something you wanted to?
No, I think so far we like today we talked about the how a matrix multiplication is done, how it's used, and we talked a little bit, in a very abstract way, of how it kind of means in a physical space. Maybe sometime later we can express that. Like we took out the iPad a little later. We could have shown the bending of the space a little better.
I'll have to watch
that way.
that 3 Blue Run Brown.
Yeah,
so
but
to get a better grasp on it.
Yes, you should definitely do that. And they have fantastic, beautiful animations.
Oh yeah.
And I was so inspired by their animation skills that I actually YouTube this, how to make videos like 3 Blue 1 Brown.
Oh, nice.
And they have an API for that. And 3 Blue 1 Brown, I think they made it to do all those visualizations that they do with math. Well, it's amazing.
Very generous of them to share it with the world like that.
Yeah.
That's cool.
All right. So I think that's it.
Yeah. Next time or some other future time, we ought to talk about why matrix multiplication is so heavily used in machine learning. And what is there a more general thing underneath matrix multiplication? Because what we showed so far is we start with the multiplies and then we do the adds. Does it have to be always multiply and add? Maybe not.
Maybe not. And we'll know and future.
Yeah.
In later videos. All right.
Great,
Thank you.
thanks.
Bye.